but
So this is all in C, right?
everything is in C.
Okay.
Is in C. And CUDA is like you will see is a superset of C. So everything will be on C. So let me see.
We usually run all our GPU stuff in Python because they have Keras. Keras loads into
Yes, but that, let's say, you are not actually programming anything in CUDA, or so. So
using.
the idea is to go into that direction. So what I will be doing, this is what I will be doing today. I will be first starting to demonstrate what parallel computing is. So the big picture first, what parallel computing is, and the different models and the different paradigms and the strategies that people have developed over the years for parallelizing codes, for working on parallels. So today I will be just introducing the different concepts that, even if not exactly what we will be using for CUDA or for GPUs, they are needed to understand how you program a GPU, how you program that kind of device. Because on CUDA, you are basically dealing with thousands of computing threads. On a CPU, you basically deal with a much smaller number of multi-threading. So the concepts there are needed to extrapolate those into the big picture of working with GPUs, and also how you move memory from one place to another. So that will give you an idea at that, let's say, low level of that. Which at some point we will be moving into CUDA, and later going up into high-level languages. And I expect at some point in the second or third lecture to explain at the very high level, like Python, like how you work with PyCUDA, for example, and with all that understanding how you actually work with those high-level packages that have been developed for on top of CUDA or on top of GPUs. So like TensorFlow, like Keras, like PyTorch, all that stuff that is very, very high level. So when you are working with those things, you are not actually programming anything. It's just following the recipe for building a neural network or a deep learning structure, which is actually something very simple. It's actually very easy. So this one is, and on that respect, it's much lower. Wait. So before I start with that, okay. So, okay, let me see what I can do. Okay, so I will be sharing my screen here. Which one, actually? Okay. Okay. So let's start with this. Um, by beginning of the 21st century, a couple of things start happening on the area of HPC, high performance computing uh, the domain. So one is that mainstream CPUs start getting multiple cores because the manufacturers, Intel in particular, AMD, got a constraint on the ability to make the cores on those CPUs faster. They cannot increase the clock on those chips, because increasing the clock will also increase the power consumption of those devices, which in turn increases the amount of heat that they produce. So they came to a realization that if they want to increase with the piece that we're doing until beginning of the 21st century, at this moment we will be dealing with a GPU with 10 gigahertz or something like that. And that basically will produce a heat, a temperature that is pretty much close to the nuclear reactor, 20 gigahertz at that scale will simply melt the chip. So the solution for that was, instead of increasing the clock speed, what they do was to add more and more cores, basically replicas of the original CPU in an arrangement inside the same chip, and also miniaturizing the whole thing. So that basically lowers the power consumption, increases the area, and basically improves the heat dissipation on the whole thing. So basically there is a thermodynamic constraint on all that. That's one trend. Another trend that started emerging pretty much at the same time was that all those GPUs that got very popular thanks to the gaming industry, basically. So the consumer industry drive a huge market in volume for GPUs. And at some point, people realize, okay, well, these GPUs are doing things that could eventually be also useful for doing numerical computation. So why not to use those? They are becoming cheap. They have many cores. Those cores are very simple. We will see that today and next week. But we can do something with them. So with all that, CPU cores with more, with increased number of cores inside them, and GPUs, and in general, what is called a coprocessor. So not only GPUs, but basically 10 years ago, or something called Intel Xeon Phi coprocessors, which basically were Pentium Pros of all processors packed together in like 50 or 60 of them to make computations. At some point, Intel abandoned that project, but many of the ideas that were put in place for the Intel Xeon Phi are right now inside the CPUs that we have on Thorniflat. So the AVX 512, for example, those extensions for the CPUs were created inside the Xeon Phi. And the fact that we have 40 cores on a machine is, in some respect, a consequence of all the developments that were done for the Xeon Phi coprocessors. And nowadays, we have basically a market dominated by multiple cores. You see, Thorniflat, we have 40 cores on each machine, and GPUs. And in the future, we will have not only those GPUs, mass FPGAs, and in a few years, from 5 to 10 years, the idea of neural processors will become more mainstream. So basically a new kind of processor that mimics, to some point, how a neural network actually works. So it's a chip that is actually mimicking the behavior of a neural network in hardware. So in this lesson, we will be concentrated in two models for using GPUs. So one is CUDA, another is called OpenACC. Those are low-level things, so we are far away from TensorFlow, for Keras, for all those high-level packages that were built on top of that, and will be on top of CUDA. So dealing with GPUs, it's important to understand that GPUs will not replace CPUs. There are a big set of tasks for which CPUs are the solution, and there is nothing nearby that will tell us that GPUs will perform better for those tasks, for several constraints, basically. The cores inside GPUs are very simple. They are very simple structures, very massively, but very simple. So they don't have the whole capability that a real CPU has. One thing. Another thing is that they have their own memory. So when you buy a GPU, your GPU has a certain amount of memory inside that car or the box and the envelope of that GPU machine. So and the GPUs can only see the memory on that chip on that car. So when you are programming, and this is something that will be very evident in the next episode here, you need to send all the data to the GPU, which takes some time, do the processing, and take all the data back to the host memory. So all that process of sending data and retrieving data takes some time. If the amount of time that you take moving the data is larger than the amount of time that you take computing the data inside the GPU, it will not pay off. It will not return any positive outcome, extra performance doing that. So in order to grant that you get something out of using a GPU, you have to do something that sends a certain amount of data from the host to the GPU device, do all the processing there, and only at the end taking the data back to the host. That's one of the biggest constraints that we have when we are thinking, okay, which kind of algorithms, which kind of things we can move from CPUs and offloading into GPUs. So we end up with a situation where right now we have several models that uses CPUs plus GPUs plus other kinds of coprocessors, and we will be exploring today basically all those a set of those alternatives. So for those of you, I don't know, Alfredo, I know the other guys because I asked last week. Alfredo, do you know C? Are you familiar with C or so?
I mean, I know C from like a long time ago, but I'm not. I wouldn't consider myself efficient in C.
Okay, so what I will be doing today is in the next section here is that I will be discussing a C program. So I will stop a little bit describing a little bit. So I prepared on a small program that basically contain the basic that you need to know how you program a C code. And I will using this serial code in order to start introducing the concepts for the other models of program. So, but before that, let's talk about Thornyflat, what we have. Here in the picture, we have an image on the PCI version. So, of course, for you, you have a different version of your, a kind of similar, but the model for a laptop or something is slightly different. Of a card with an NVIDIA, this is for a Quadro RTX 6000. This is our latest models of cars that we have on Thornyflat. So you have the chip and you have all the devices around. But the important here is to capture a few numbers here that even if we will not be going into much detail about what each of them means, it's important to capture some of the wording here. I am basically comparing here the two cards that we have on Thornyflat. Our first generation of cards that we have on Thornyflat were those PIC 6000, and now we have RTX 6000. They came from different generations. So NVIDIA have been adding names, and those names have some meanings on the terms of the number of cores or tensor cores or all the stuff that they have on those machines, and the abilities to manage double precision, single precision. So on Spruce, we have by today all GPUs. They are from the Kepler generation. On Thorny, we started having those Pascal generation, and now we have these new cards from the Turing generation. Okay, next thing, inside the GPU, they have a certain number of cores. And by no means you can compare this huge number of cores with the number of cores that you have on your CPU. So part of the reason, as I told you, is that a CPU is a much complex structure. They have a lot of things that a CUDA core will never have. However, they came in a huge number. So it's 4,000 here, 4,600, and almost 4,000 here. So all those cores are able to do concurrent operations. All of them are able to go into the memory and start doing operations with that, with all that memory. So there are also differences in the clock speed of the memory. As usual, when you get newer and newer machines, not only the CPU gets faster, or you try to get it faster, not necessarily with the CPUs, but at least the memory have been increasing. So you know, this, let's say 10 years ago, with the kind of memory that we had was running on 1,300 megahertz. And now we are probably around 2,000 megahertz. It depends. But,
Guillermo, can I ask a question real quick?
yes.
So I know when you deal with like multi-core processes, that each thing has threads, and I know a CPU is different from a GPU.
Yes.
But these different internal cores, can they be like hyper-threaded, or because I know they're super basic, so my guess was
yes, no. Yes, they are doing multi-threading in the CPU, in the GPU way. Okay. So those are threads, and they are called threads, and they operate, and the basic understanding of multi-threading works here. That understanding that on your machine, I don't know how many cores you have, CPU cores you have, but let's say 16. So you are dealing with 16 threads. So if you are operating with OpenMP, we will see an example of that in a minute. That's what you have. 10, 20 threads here. And here we have 4,000. Okay. And when we are programming this, we don't even care about this number. We create a much larger, and eventually a much larger number of threads that goes beyond this number. And the hardware will take care of that huge many threading operation, and will assign all those threads to those physical hardware GPU cores.
Yeah,
When
which
it's
is done by the scheduler, right? I mean, same thing when you even do parallel on a CPU, right? You can give it,
yes,
you know, 100 things, and if you have, 15 cores, the scheduler will take care of how that's done,
the
right?
scheduler will take care of that. The scheduler and your CPU, and in this case, the scheduler on the CUDA device. However, when you are doing multi-threading, numerical multi-threading in the CPU, there is a problem with that. If you put more threads that are numerically intense, uh, you could end up in a situation when you are underperforming. And the reason for that is that if you have imagine that you have just 4 cores on your machine, but you are asking for dealing with 8 things. So basically what you're doing is to assign for a few milliseconds one thread for doing something, and the scheduler will stop that and give some time to the next thread, because you have more threads that cores on your system. And every single time that you are stopping and giving the preference to another thread, you will be discarding parts of the memory that resides on the cache. And the cache, is a very limited portion of memory that is very fast. But discarding all that memory have a penalty in terms of time. So you are discarding a memory, and you have to bring more data from the main memory to the cache. All those discards end up adding time. So at some point, if you ask for 8 threads for a numerically intense threads on a machine, you will end up taking more time to complete than just asking for 4 threads on a machine that has only 4 cores. So, however, CUDA, and this is the way that those cores work, they are much more efficient working with this extra overload, so over subscribing of execution that CPUs are capable of. So the scheduling is different, and you can put more pressure on a GPU than the pressure that you can put on a CPU. That's the main point. So now, GPU memory. So basically, we have the same memory on both of our cards. Here, 24 gigabytes. That's good enough for some people. It's not good enough for some other people. So that means that all those cores you can put at maximum, you can put 24 gigabytes of memory. And again, this is important, and this is part of the price tag on those things. So you can get cheaper machines with less amount of memory, but you are also limiting in your ability to put those CUDA cores, max them out, thanks to that limitation. So I think this is a high number for today, 24, but they are bigger and far more expensive GPU cards with more memory.
Two questions again.
Yes.
So number one, I always hear this term called VRAM. Is the GPU memory considered the VRAM, the VRAM?
No, I think that you're well, several things. There is something called NVRAM today. That is a new technology that appears. It has been announced for a few years, but now it start getting mainstream and start you getting. So it's called NVRAM, and that NVRAM means non-volatile random access memory. So it's basically RAM that is fast enough and look and works similar to your SSD hard drive. So it's like an SSD hard drive with the speed of RAM. So it's non-volatile. So that means that you can switch that computer off and the memory on those chips remains. So like in your SSD, you turn off your computer and the data is still on your SSD hard drive. But you turn off your computer and all the data on the RAM goes, disappears. So that's what is called NVRAM.
What Alfredo was referring to is right, though. It is like the thing you're pointing at right now is typically called VRAM.
And
like video RAM or something like that.
Yeah,
oh,
that's
that's
pretty much
probably
what it's
the video RAMs. Yes, yes,
Yeah.
that's so. Yes, so.
But like, so yeah, people will say for that RTX 6000 card, they'll say it has 24 gigabytes of VRAM. That's the same
Okay.
thing.
Oh yeah. Okay. Thank you then.
All right.
Yes, there are things here that as they came from the world of let's say using these cards for the original purpose that was graphics for play for gamers basically originally. So the mass market and I think that there's still HPC is just a niche market for NVIDIA. They are trying to make it bigger, but they are getting much more. The real money comes from the huge number of gamers buying those cards from the latest.
Yeah, I may have just spent $700 a couple weeks ago.
Okay.
3080, right?
Yep.
For a new card, for a new
Yep.
graphics card.
Yeah, for the new ones.
I might have spent some money on graphics cards for computer games at some point. I don't know.
So you say you send a not negligible amount of your paycheck to NVIDIA
Exactly.
or those manufacturers. So yeah, you see all those companies are in a big chunk. They are driven by consumers. This is they are not paying thousands of dollars for a graphic card, but they are many paying a few $100s for those graphic cards. So that's why many of those things are concentrated on textures, or on what now you see the new consoles for gaming. They are doing ray tracing, reflections for making a more natural environment for those games. They look, the lights are actually, they compute the like rays, how the light crosses different surfaces, how they reflect and transfer. All those calculations are happening on those devices. And of course, the traditional things that those devices do, are basically rotating triangles and all that stuff. That is basically linear algebra. If you think about it, what you are doing when you are rotating an object, you are rotating the space around, you're basically computing linear algebra. You are entering with the rotation matrix and applying all that rotation matrix over and over and over on all the points and all the triangles that build the surface of the objects. So that's one thing. So you notice they consume an important amount of power. So this is 250 watts is pretty much the amount of consumption of a normal PC without those GPUs. So the entire GPU consumes pretty much the same amount of energy as in a normal computer. And then a huge amount of energy, several times what the consumption of a laptop, for example. That's one. Another thing is there are here a couple of numbers here about what level of CUDA the cards support. So for this case, the RTX 6000, the P6000, they support CUDA 6.1 and OpenCL 1.2. we will get an example of CUDA and OpenCL in a minute. So I will see what how we go with that. So now, knowing what you have on your computer, and you can do this, for example, on your machine. Alfred, you know that you have GPUs on your computer. You can just execute this command. If you have the CUDA toolkit, you execute this command and you get the number of and the kind of cards that you have. So on the first generation of GPU machines, we have three cards here, P6000. We just installed the latest version of CUDA on all those machines. So we have 11.1 and the driver on the kernel, get the number for that, and the amount of memory right here. So 24,000, so 24 gigabytes of RAM on every single card. So, and the amount of energy that they are consuming out of the top of that. So that's what we have on our first generation machines. So all those machines, we have, I think it's like 7 machines, they have exactly this configuration, 3 cars. On our new machine, we have one, for example, that has 8 GPU cores. So this is our most impressive machine, let's say. It's an RTX 6000. Again, it's supposed to be 24 gigabytes of RAM anyway. And we have 8 cores here for them. Okay, so now we will start exploring that. I decide to do this, to move a little bit away from CUDA and OpenACC and move a couple of steps back to review C programming a little bit, and OpenMP, MPI, all the different models for parallel programming. So this is what I will be doing. I work these days on one single problem. So at the same problem, I will develop the code serial. So the code without any parallelization. I will explain the code, and after I will explore in OpenMP. What the kind of things that you do to parallelize that code with OpenMP. One example with MPI, one example with OpenCL, OpenACC, and finally with CUDA. So as we progress, you will get, for the same problem, a flavor of the differences and nuances of the different models of parallel programming for that. So let me describe the problem, and I will show you where I have the data. So let me see if I can, or I can paste here. So the data is share software. So you can go here. I will paste this on the on the chat. That is the location. So you can take all the code that I will be showing today from this location. I will continue on the web page, but for each code, I will show you how you compile and execute that code and the kind of things that are happening with that. So this is what I'm doing. I select a very simple and very common operation that is called DAXP. That name came from BLAST. So there is one library called BLAST that was created back in the 70s, I think. BLAST means basic linear algebra. So it's the lowest level of linear algebra routines that originally were created in Fortran 77. It's a long time ago. And they create a bunch of routines. One of those is DAXP. The name DAXP came from double precision, that's the D. They have also a SAXP and also CAXP. So they have single precision, double precision, and complex, and double complex precision. So they have 4 flavors of that routine. So in here, I will be using the double precision for all the examples of a number, A, that is multiplying a vector or matrix X plus another vector Y. So that's the name, what is called DAXP. And it's in BLAS. So there are a set of routines that are very popular, or popular, not, people have been using this for decades. From my my professors, they learned that. So back many years before me. Who create 2 sets of libraries. One is called BLAS, and on top of that, there is something called LAPACK, BLAS and LAPACK. BLAS is basically linear algebra routines, like vector multiplication, scalar vector multiplication, matrix multiplication, all those sort of basic operations in linear algebra. And LAPACK deals with operations like inverting a matrix, computing the determinant of a matrix, decomposing a matrix in triangular, superior triangular, lower triangular, decomposing the matrix in several forms. All those higher level operations are in LAPACK. So I took one of those operations, and I will be using that as an excuse for presenting several concepts here in parallel computing. So this is what we are solving. And the problem that we basically will doing is basically computing this. So the cosinus squared of an array minus the sinus squared of the array. This is a trigonometric equivalence for the cosinus of the double matrix. So it's something that it will be, it's simple, but still you can see the results and you can make sense of them without too much effort. So an X will be an array, and no matter how many elements you put in that array, I will be putting real numbers that goes from 0 to pi. So we'll be covering one cycle here. And let's start with how you access the compiler. So I will be jumping here into this screen. Let's see how it can change my screen share. Okay, so now I'm here on Thorny. So let's start with this. As we will be using the, okay, first, QStat. You want to know which queues are available on a machine, you execute this command. You can see that there is here one queue. Here is this. We will be using this queue for launching an interactive job on by the way, we will see if we get this.
Quick question, Guillermo.
Yes.
So I've pulled this up before, and for example, like, you know, on the one you just said, the COM GPU, whatever, it says 0, 0. So does that mean there's one available? Is that like how we know, or what?
No, that will not tell you how many are available. This table here will not tell you anything about availability. It will tell you just the number of jobs allocated on those queues. But having that, and that will not tell you directly anything about if you get any better chance or not of getting your job on that queue. For example, standby. Standby, you see 142. Okay, that seems to be a large number. But there are many, many machines assigned to that queue. So that number is not that big in the context of the number of machines that are able to process jobs that have been allocated to that.
So what could we run to see like what is available?
You can do several things. One is one is executing this. For example, you submit a job and your job is in queue, and you would like to know when the job potentially could start execution. So there is this command, job start. Let me see if I can get something. QStat. So do you have something, by the way, Alfredo, or not?
I don't.
Okay, so okay, so here there is one thing. So I will be picking this. Notice that this one is in queue, is in the small. So I will be picking this number. So this job ID. And you can show a start. Well, it's supposed to be running. But it's still blocked. I pick a bad example. Let me see another.
Was that because that's a batch job?
No, this job is blocked, and I don't know why it's blocked. So block means that job doesn't have the resources for running, and I don't know exactly what. Maybe this job is waiting for more resources. Check.
I wonder, Guillermo, if the only nodes available are the 20 core nodes and not the 40 core nodes.
No, I don't understand that. So he's just keep asking for one core, for one node, right? One node, all the 40 cores, and I don't know. Wild job.
It's okay. I was just looking for a quick answer. I don't want to
Okay.
take away from the lesson.
Okay. So yes. So the main point is you will not get answer to your question from this table.
It's okay.
But indirectly, yes, you can get it. So if you know that the standby, you have 142, you say, okay, this job has a very reasonable number of jobs for the amount of nodes that are assigned to it. If you see 5,000 jobs on that standby, you will be starting being concerned. Okay, someone put too many. But even with that, you get the chance of getting. If someone just submit 5,000 jobs, it doesn't, and before you, it doesn't mean that you have to wait for all those 5,000 jobs to finish before your job start running. Although some of them will be blocked, so they will be not running and not accruing preference by not being in execution. So the system will balance the priorities. Yes.
I was gonna say, looking at standby right now, there are 134 of them that are held, and there are none sitting in the queue. So you probably have a good chance.
Oh yeah. I don't know why.
It's probably Kyle.
Okay. So what I will be doing right now, you can do this exactly. So you will be entering with me. Is using this queue, and I will be nodes equal 1, GPUs equal 1. So I am requesting just one GPU And if you want to be completionist, I can do, okay, something like, no, actually I will request, how many we have? 8. Okay. So
Yeah,
I can
how does
do
that
some.
work? I know when you get a compute node, you have like multiple cores on that compute node. Does the GPU have like, how does that work?
You can request a number of GPUs and a number of cores. So I'm requesting 8 cores here because I will be demonstrating a few parallelizations that are purely CPU. And the first share for that machine is actually 8. Okay, so the compute node, that compute node has 24 cores and we have 3 GPUs. So in order to be fair with everybody here, imagine that 3 people will be able to get access to this. I don't know if you can tell me. If not, maybe Nate can give us a hand just in case. My first share of CPUs is 8. 8 cores for 1 GPU. So 3 GPUs, 24 cores. But you don't have to do that. You can just sometimes some codes are very GPU oriented. So they will use the GPUs and they will basically not use the CPUs at all. So it all depends. But the idea is to always request no more than the first share of CPUs, of course, that you have available on that machine, taking in account the number of GPUs that the machine has.
Yeah, so I guess my question is, like, you're still technically on a compute node, so you're on a CPU, but then that CPU has access to the GPU.
Yes.
Okay.
Yes.
Okay.
So the access is so right
Well, I mean,
now
the GPU nodes come with CPUs on them. So there's 24 CPUs to the 3 GPU node.
Yes.
For the purpose of having 8 cores to go along with your GPU.
Yes.
Okay, so this is like a separate GPU node.
Yeah, there are nodes specifically just for GPUs.
Okay.
Yes. Okay.
I thought we were on just a regular compute node.
No, so the
You could be on
cores
any
that
compute node, and then it goes to the GPU.
yeah, the
no,
cores
no,
that
no.
Guillermo's pulling from are one specifically for GPUs that are on the GPU nodes.
Right.
Okay. So no, and now I got it. I got the point here. We have 2 kinds of compute nodes on Thorny: machines that has GPUs and machines that doesn't have GPUs. There are just a few, 7, 8, probably, I think less than 10. I think. Correct me if I'm wrong, Nate. Machines that have GPUs inside them. Most of our machines do not have any GPU inside. So I enter in one of those machines. So I got assigned, when I execute this command, I got assigned one. I jump in, the system will jump me into this machine that has 3 GPUs, but I request just 1. So it will only allow me to see 1 GPU. So I see 3. You can see the number of CPUs with this command, proc CPU info. So you see that I have 20, start from 0. So it's from 0 to 23. CPU cores, and you get information about which kind of CPU core is. In fact, what we have is a machine. Imagine slab box where we have 2 sockets. So 2 CPUs of this kind. And if you go and search on internet for this Xeon Gold 6126, they have 12 cores per chip. So we have 2 chips inserted on that machine. So 2 sockets. So we have a total of 24 cores on that machine. Most of the machines have 40 cores, so twice 20. And we have new machines with 20 cores, just 20 cores. And you see here the cache, for example, for the CPU. Very fast memory that is very precious. And if you notice, just a sideline here, the size of the cache is pretty much the price that you pay, the extra price that you pay when you move from those Intel Core i3, i5, i7. One of the important things that change from those different consumer level CPUs is the size of the cache. Cache is very, very expensive. So
because the Xenon's technically a server CPU, right?
yes, the Xeons are for servers. Yes, so they are also a different market. So they are not for consumers. Even if you can use, you can buy those, but typically they don't. They don't put those CPUs on a consumer level machine. They go for workstations or for professional machines, let's say. That's the point. So you can execute this command and you get an information about what you have on your machine, where you get assigned here. So now I will be working on, let me see, Scratch. I will be doing exactly what I was expecting for you to do.
All right, one last question, Guillermo.
Yeah, sure.
So since there's 3 GPUs on the machine, and you don't have to use all of them or the cores, the CPUs, can there be more than one person on that node?
On that GPU, you mean? On that node?
On that GPU node, yeah.
On the GPU node, yes. On the GPU, on the node that has GPUs, yes. Several people, 3 people actually, that request 1 GPU can be at the same time working here on this machine.
Okay.
But no more than 1 can use a given GPU because we have exclusive access to the GPU. So 1 person can request 1 GPU, get inside this machine. Another person requests 1 GPU, gets this machine. Another third person requests 1 GPU, gets this machine. 3 people on this machine. Okay, so now I will be copying here on my Scratch all the examples that I have in software, mini workshops, GPU computing here. So I will be making a copy of all my examples here. Okay, so I can go here and you will see all the examples. We will start with this one. And we'll be doing, instead of jumping back and forth between this and the web, here directly, the serial code. Okay, let me see, here I can go. Can you see this clearly? Is clear enough, the screen?
I see it fine.
Okay,
Good.
Okay, so let's start with this section. Oh, wait. Okay, so I will mark it. This section. Let's start with this. Okay, first, when you program in C, you are programming in a text file. You write a text file like this that contains all the instructions for your program. Same thing that you are programming in Python. They have, it's also a text file. There are other program languages that when you are moving icons, for example, the kids, they learn today something called Scratch. Interface for programming that is good for kids. But in C, you are basically writing a text file. Now, the first lines here, the first line, all these lines that start with a sharp, they are not interpreted by the compiler. They are interpreted by something that happens before the compiler. It's called the preprocessor. What is, you can think about this like searching for this file in a location that is known for the compiler. And this file is called a header. And include and paste whatever is inside that file, replace that and paste it here. Take this file, search for this file and paste it here, and all this file and paste it here before you compile. So it's replacing all those 3 lines with the contents of these 3 files here. And those files are called headers. They contain the promises of what a function do and how, and which are the arguments for that function. So I need this one. What I need this one? Because at some point here, let me see. Let me see. Oh. I need this one, stdio, because I am calling this function. This function is there. You don't believe in me? You don't need to believe in it.
No, I get it. It's like in Python when you load modules. I mean, it's just that's calling the C version.
It's the equivalent of loading a module in Python.
Yeah.
So, but again, you don't have to believe that this function is there. You can just execute this. Well, not this one. Man, I think it's 3 and 3 printf. Man, 3 printf. Okay. And you get the Linux programmer's manual, and here it says, okay, all these functions in C are included here. So you need to put this if you want to use any of those. And basically this include will tell, okay, how a printf works, what it receives and what it returns. That's the reason why I have this first header. Now, next one, this one. I need this one because I am doing a malloc here, and because I am using this variable, this kind type underscore t, and because I am freeing memory here with the function free. So for those 3 reasons, free, malloc, and size underscore t, I need this header. And I need this math header because I will be using the cosinus here, the sinus, sine, cosinus, and I will be using a constant for pi. So those 3 reasons, I need this. Now, this defined vector size is something that enters in action with the preprocessor. The preprocessor will take any place here in this file and will replace any place that is not a constant string, and will replace that vector size for 100. So the compiler will never see this vector size. The compiler will see here 100 instead of this. Instead of this name here, the compiler will see just 100. And this is a good way of having a code that where you can replace this number once and having that effectively change everywhere in the code. So with this, those are the reason for all these 3 lines, preprocessor lines or preprocessor directives. Now, this line indicates that this code here is the main code for the program. So it should be able to work. and she will be able to produce an executable, a program that you can run. You can have C code that doesn't have this, but it will create just libraries. It will create functions that you need to call somewhere else. But this is a program, and so we have this. And this is a program that can receive arguments from the command line. We are not using that, but the canonical way of putting it is like this. So the number of arguments and the list of arguments that you enter in the command line when you execute. Now, different from Python, in C, you need to declare the variables. And that's what I'm doing here with all those, all this section here. I'm declaring the variables. So the variables are integers, int, double precision, so mean truncated real numbers. This variable from an external kind is size underscore t, that ends up being something like an integer, but they change the name. And an array, a pointer, in C terminology is called a pointer, but let's call it an array. This is an array of double precision numbers. And I have 4 of those here. So 4, I mess up this, but let me get out and get it. Double precision numbers, arrays. And now I'm doing here the allocation of the same line. So I'm here allocating a certain number of bytes. I need to ask, okay, how many bytes do I need to get a double precision number for this architecture? Okay, and now I need this number, 100 times this number of bytes. And I need to allocate that space in memory because I will put in that number for the X, A, B, and C. So I'm allocating all that. And now here I have 2 loops that I on purpose separate for reasons that will be evident later on. Here I'm doing the initialization of that. So I will declare in the value of X. So notice that I'm starting here for a value that is close to 0 up to pi. And here, this is something, this is an excuse for me to show you that you can do this kind of things in C, pretty much the same as you can do this kind of things in Python, erasing the values of the array by way1. You don't have to do this. You don't have to erase. If you don't erase that, they will contain all the garbage that is in that memory location at that moment. You don't care because the next thing that you will be doing in this loop is overriding that array with real values, with values here, the cosinus. A side note here, usually this is more efficient than writing cosinus star 2. There will be a square. The exponentiation operation in general is a very expensive operation. So if you can replace that with an actual multiplication, it's more efficient. It's a small trick in programming, but you will see often that people write x times x instead of saying, oh, why is not writing x squared? It's because x times x is more efficient to, and even x times x is more efficient to do than computing the cube now. So they will go into different. Sometimes compilers are smart enough to realize that and do, probably modern compilers for simple cases will realize that, and okay, it's better if you do it this way instead of actually computing the square of the variable. Yes, anything, Alfred?
No, I was gonna say, yeah, I know that trick.
Okay.
I've always heard that the 2 easiest ways to make your code faster is to take off any squares and then to multiply anything vectorally if you can.
Yes, yes, yes. That, however, that message comes with the caveat. Compilers today will probably do that for you, so you don't have to even to worry about it. And here, what I'm doing is just an excuse. Again, it's an excuse to show you in C how you make a conditionals. So I'm basically evaluating if I have a small vector, it will be okay. I will print out that vector. It's okay. If the vector is too big, if I am changing this, and you can try to change it for something like 1 million, just to explore how this behaves. You can do that, and at that moment I will be just showing the last 10 numbers. And this is the way, this is again very similar in Python. We have this kind of format. Actually, the format in Python comes from C. How you write numbers, real numbers, with a certain format. So this format means separate 9 characters for the number with 5 decimals, and this number will be a floating point number. And just write a number. If you replace this F by E, you will be writing that number in scientific notation.
Yeah,
that's another option. And another value is for integer, instead of F is D, for strings is S. So with this, you get a super fast, and here at the end, I am releasing the memory for those arrays. When you don't do this and continue doing other operations and you forget about doing this, we have what is called a memory leak. Portions of memory that are not being used, that you will never use, and they sit there forever until the end of the program. Not a big deal in this case because we are ending the program anyway. But this is a source of failure, or at least why my code is gaining memory and memory and memory, and at the end crashes, is because very likely you have something like this. You don't have something like this. You have arrays that you never deallocate, and they grow, and you create more, and you move pointers. You can do a lot of things with this. And you get portions of memory that will never be deallocated. So yes.
Question, Guillermo. So when higher level languages like Python and MATLAB and all that stuff,
yes,
do they release the memory for you in their routines, or
they have those languages? They have what is called a garbage collector. So at some point they realize, they check which portions of memory will not be accessible anymore. They will not have any way that memory could actually be called again, and they just discard that memory. So they have like a small machinery that do that for you, and that's called garbage collector. There are some other languages, they don't have garbage collectors, and they have other ways to protect the developer, the programmer, from doing nasty things. But yes, in the case of Python, they have a garbage collector. Okay. And some other language have garbage collectors. Okay, so we have this. I will be leaving this code. And so let me show you, at least for this case, how you can compile this code in multiple ways. But later, I will be concentrated on just one module. Okay, without doing anything, this code is so simple. Let me see, module list, that I don't have any module loaded here. So I can just compile this code, taxp serial, and okay, and here -lm, and I can compile it. So
what does -lm do?
Okay, the reason for the -lm is because I using an old version of GCC 4.8. I will double check my statement here. I think that you don't need it for other versions of GCC later on. And this is basically including the math library. Notice that in the code, daxp serial C, you will have this,
Oh, and that one doesn't have the GCC.
and that is not inserted by default. Those are inserted. You don't have to do anything. You just put this. But if you are adding some other stuff, you need to explicitly say, okay, I insert this library, and this is searching for the math library. That's the whole point.
So is that loading math, or is that just loading from the includes?
It's adding, okay. It's adding, the header is added to the code that will be compiled. That's one thing, the math.h. But here is adding the library so it knows how you implement the sinus and cosinus. So the actual implementation of the series is actually serious. What you do to compute a cosinus, what you do is basically a series. You compute several terms in a series that converts into cosinus, and several terms in the series that converts into sinus.
No, I get that, but I'm saying what the argument's doing. So is the argument saying, look at the includes, like the headers?
Yes.
Or is LM adding specific?
No, it's two different things. One is the header. The header is just the promise. Yeah. How you need to compute the cosinus? What you need? Okay, you need an integer. Okay, no, you need a double precision number as an argument, and it will return a double precision number. So that's just a promise. Let me see if I can get this here on the manual. 3 cosinus. Okay, so here. This is what you get in the math.h. Just the promise. Okay, I need a double and I return a double. You give me a float, I return a float. You give me a long double, I will return a long double. And the name is different, cos, cos F, cos L. It's just a promise. It will not tell you, this math.h will not tell you the algorithm that is used to return the cosinus of a value. That functionality, all that machinery is in a separate library. It's a file, it's in a different file. It's not the header who is doing this. And that is the math library. And that is what you are inserting when you compile it this way. It's looking for a library that is called lib, and probably will not, it will, this is an exception probably in some compilers. It will not, for other cases, it will be looking for a library, something like, if I execute this, for example, LGSL, something that you are probably familiar with. LGSL, if you are using it, is looking in certain place for a library that has this name, lib, this name first, gsl.a or .so. That is the meaning of this LGSL. It's looking for a file, always with the beginning lib, and whatever you have written after that, so LGSL, that's the name that it's looking for.
Okay.
So I input in something like this, QWERTY. If that thing exists, is looking, well, that is looking for something that is called QWERTY.a. Okay. That's the name it is looking. Or QWERTY, that for a static library, or that for dynamic library. So that is what it's doing.
The LM is specifically calling that math.
It is specifically calling the math library, all the functionality for sinus, cosinus, all whatever is in the math library, it will be incorporated. Okay. Actually, we'll just pick the cosinus and pick the sinus and insert that into the final code. Yeah. So it will search for that. The constant pi is in the headers. The constants, all that stuff is on the headers. So we don't have to worry too much for the constants. For the functions, yes, you have to do something like this. LM. Okay. So now another option, and I think, you can also compile this because it's C code. You can also compile it with a C++ compiler, and in that case, the C++ compiler insert the my library by default, so you don't have to put the lem explicitly. And now let me search for another alternative module, load lang GCC 10. Now we have a different version of GCC 10.2. This Now let me see if I can compile this, so it's also forcing me to. Okay, the answer is with the same thing. Yes, so yes, it will not be able to compile except if I explicitly put the -lm for this.
So question on the GCC part.
Yes.
So the GCC, when you type that in there, that's the whole you know, I don't know the right word for it, but it's the whole like the whole suite of them, right?
This one is the whole suite.
Yeah.
I am loading the whole suite. GCC is the name of the command for the C compiler included in the GCC. So it's GCC means GNU compiler collection.
Yeah, the collection. That's the word I was looking for.
GCC lowercase is the GCC is the C compiler. The C compiler that in the GNU project. So
you can still call C++. You can call G++ as the G++ one, right?
Yes, you can still compile. In that moment, you don't need this. It will be compiling. I will be compiling with the C++ compiler, and it will be just fine. So that's one thing. But I don't want to use that, for example, and I can load another compiler, load lang Intel, for example, 2019, and they have a different C compiler. It's called ICC.
Yeah.
That's the serial. Oh, okay. But I cannot compile it here because I can only compile C code because I need to communicate with the license server, so I cannot do it here. But that's the way to do it. A module purge, and I will be using just this compiler here for module load, lang, NVIDIA, HPC, this, MVC, DAXP serial C. Okay. So a few weeks ago, I installed this compiler, the NVIDIA, the new NVIDIA HPC SDK. And the reason why I will be demonstrating everything here in this time that we have related to using this compiler is because this compiler will give me everything that I need to demonstrate OpenMP, OpenACC in particular, OpenCL, and I can also separately compile with CUDA. So that's the reason why I will concentrate on this. So this is MVC, so that's how you compile a code with this, and you execute it this way. Now it's basically showing AX. This is the cosine squared, and this is the sine squared, and this is the difference. So it's showing all the values here. So now let's start moving. The time is short. Let me see how far I can go. In 30 minutes is OpenMP. Now, the code is basically the same thing. So I don't have to explain much. Now that you know how you write code in C, I just need to explain the difference. And the difference is this include here and this pragmas here. This pragma here with eventually with this function here, and this pragma here with this function here. So OpenMP is an excellent, very cheap way of parallelizing a code with minimal changes on the sources. It's very, very easy to use, and you can achieve amazing parallelism with very little effort. So what I'm doing here is I am importing this because I will be using this function. If I don't need to use this function, and I don't need it, it's just for me to show some messages here, it's perfectly fine not including this. Now, this pragma here and this pragma here are the clues and the tricks for parallelizing this code. What I'm doing here is I'm saying, okay, this is a comment from the C perspective. So C language will not complain, will not be angry about this line, because from the point of view of C, this is a comment. It's completely ignored. They don't pay attention to this problem. A compiler that it understands OpenMP will read this and see, okay, someone wants to do something here, a parallelization here in OpenMP, and I will parallelize in a for loop. These variables A and B will be the same for all the threads that I will be creating, all the multi-threading here, but these variables will be private. So please do a copy of those variables, separate for each thread, because they will not be shared. So a portion of memory, it will be shared between all the different threading that will be created to compute this. And some variables will be private, they will be individualized for each thread. And I'm using this ID for getting a number that identifies the ID or the identifier for that thread. So I can print something like here, okay, I'm working with this, I'm working with this. So a small message here. And more important here, I am populating the X, A, and B in parallel. So all those computation of cosine, sinus, square, all that is now done in parallel. So all this big array is populated with several elements concurrently. So we are gaining something out of this parallelization. And now this, that eventually, not in this case, but in real non-academic case, this is actually the real thing that is really hard. So this is what you want to parallelize extremely, is also parallelized. So in this case, A, B, and C are shared. So it will be the same A and B and C for everybody. I and ID will be private, and it will be assigning 10 of those I's for one thread. So one thread will receive from 0 to 9. The next thread will receive from 10 to 19, and so forth and so on. So that's how this works. And you don't have to do this way. If you don't do it, it will be dynamic. So the first will get different I's. The first who finish receive a new one. When it finish, receive a new one. So it will be dynamically allocating all that until the I is exhausted. So the whole loop moves on. And finally, I'm doing the same thing. Basically, this is just a copy and paste of the original serial code. Is just showing the vectors if the vector is large enough. Okay, so how I compile this code? With GCC, and I don't think they will work for this version, but let me try MP, F OpenMP minus LM. Okay, this is how you compile with OpenMP. Notice that it's not in the language, but the compiler, the GCC compiler, is able to compile that code. If I add this, so I execute this way, and if you see here, you will see what I told you here. There are two loops here. So here, different numbers, different IDs are receiving I with different values, and they will not appear in any particular order. Notice that this I here was printing here, and this one was printing here. So there is no ordering for the execution. There is no ordering for the results, then printing here. However, in the second loop, in the loop for the evaluation, notice that this ID equals 0 contains all the values that are less than 10. Or for example, let me see if I can, okay, here. So here I'm getting 6, 8, 9, all those got assigned to the ID, to the thread number 0. So they are gone in chunks of 10. And at the very end, I'm printing the values here. So this is OpenMP, very simple. And with MVC, I can do something else. OpenMP .c minus MP and info equal all, which is actually very nice. So this compiler is actually able to show me, okay, in here, in this line, I found a parallel region and I parallelize that. In this line, I found a parallel region, I am parallelizing that. And here it found another place, but this is not OpenMP. This is something else, I think. And it's parallelizing that region too. So it's declaring the parallelization options that it took for this code. So now let's move to something completely different, and a completely different kind of parallelism that is far more complex. That is the DAXP MPI. This is completely different and a lot of changes here. And I will probably, as this is, we will move into CUDA, we will move into GPUs. I will not make too much effort on the pages that I create for the class. I described in more detail all this. So, but I will be going superficially here. So MPI.h, something needed for compiling this. There is this section here, all this. A variable for the status that I need when I call in the receive function, but we'll see that in a minute. And this line, MPI init. When you are working with MPI, this code will eventually be able to execute on different compute nodes. So you can have 10 compute nodes. Each compute node is an independent computer. It's an entirely complete independent computer that communicate with others via network, via a very special network, but it's network. And they send message back and forth between each other to coordinate the execution, coordinate them. So this is the highest level of the most complex level of parallelism that you can achieve, or say, considering multiple compute nodes. And when you are programming with MPI, the very first line that you need is this one, MPI init. So nothing can appear, not a single routine call can appear before MPI init. And after that, I am calling this couple of functions, MPI comSize, comRank, to get the total number of processes in this MPI execution and the total and the number assigned to this process. So each process is running exactly the same code, but they receive a different number. They receive a different rank, and they can operate differently based on that number. Everything here is pretty much the same. So, but I am using the rank here in such a way that, and also allocate, I'm also doing something nice, is that I don't need to allocate the whole array for every single process. So each process is just allocating a subset, a chunk of the array, and that process will work with. Otherwise, I will be end up having replicas and replicas and replicas. And some programs do that thing, but that's why MPI programs use sometimes a lot of memory, and you put more processes into play. And at some point, the memory on the system is not enough because there are a lot of replication. But if you work out and you develop the code a little bit better, you can manage to have just a portion of the array, a portion of the vectors, instead of the whole array. And that's what I'm doing here. It's just, so I'm not allocating the big thing, not vector size, just a subset of that is just vector size divided by the number of processes that I'm working on. And here I'm using the rank to just populate what I need. And here is the operation. So AP minus BP, so it's basically computing cosinus squared minus sinus squared. All that for that subset. So it's actually working in parallel. And here I'm just a small demonstration on how you send data. So if you are not the master, in this case 0, master is equal to 0 on the top of the file. So rank 0 will be the master here. So it will be collecting the results from everybody. And I'm using what is called point-to-point communication. So vsend and RECV, so is for sending and receiving data from different ranks. So all the ranks that is not 0 will receive the data from it will be sending the data to rank 0. So this is the destination. And here I'm receiving values from the different ranks. I'm not actually collecting all that into a single array. That is something that I will eventually be like to do. But I will be just printing the values. So I'm just collecting, and only rank 0 will be doing the printing. The main message here is this is how you coordinate execution, sending messages between different computers, independent computers that have their own memory. It's a complete different way of programming. We will not be focusing on this kind of programming, so that's why I'm skipping. But at the end, I need to call this function, and this is the last function that is called on an MPI program. So that's another thing. How you compile this? MPI CC, and you compile this this way. What I did? Okay, those are just warnings because I was not actually populating the whole array. At some point, I realized that will make the code too complex to explain. So those are just warnings. So nothing have failed actually with that. And when you execute, you need to call another program for execution. It's called MPI run. And I will be just using 4 processes here for this program. And there are some messages here because I'm just skipping something here. My bears. Yes, so if you see the messages here, the first process is working with a portion of the array. Second process is working on different portion of the array. Another process is working different portion in so they are working on different. And I'm skipping the rank 0. So the rank 0 is not printing anything actually, but that's probably my mistake that I changed my idea on how I will be working on this. But so different ranks working on different portions of memory, different portions of the array, of actually making their own small array and working on that, and at the end collecting the values for everybody, and eventually it could rebuild the whole array at the very end. So that's how you program and execute with open with MPI. So now a different, also a very different way of programming, OpenCL, is this. OpenCL is an effort originally from Apple, but I think Apple abandoned that at some point. But now it's a consortium of companies who have been developing OpenCL. I don't know much the future of OpenCL now, because, for example, NVIDIA wants to push into CUDA, and this one is a general multi-architecture, multi-vendor effort for computing, heterogeneous computing. So different kinds of GPUs, not necessarily NVIDIA GPUs, could work with AMD GPUs, with FPGAs, so from different electronics for offloading execution. How this in CUDA, and that's what I included. You create a kernel here. So everything that you put inside the loop for computing C equal A minus B is now a kernel. It's now here on a string. For academic purposes, you put in a string. You can also put in a separate file, but it's much better here to put it in explicit string. Contains the kernel. So nothing really important here. Most of that is just the definition of the variables. And here I am doing C equal A minus B. So that's one thing. And a problem with OpenCL is the amount of boilerplate code that you need to write to get this done. And that's huge. So there are a lot of things. This is very general. So you need to ask for the platforms, device IDs, a lot of stuff that I will not get into it. Just for you to know that this is, let's say, this up to here is pretty much boilerplate code that for most part you don't have to do in CUDA. So because CUDA knows that it's just for NVIDIA GPUs, and it will take all of that effort out of you. But here you are doing something that it will be very, very similar to the kind of things that you do in CUDA, is allocating memory inside the device. Again, when a GPU, or you have all that memory that belongs to the GPU, that is different from the RAM that the CPU have access. So you cannot reach that memory except by calling those routines that will do that operation inside the GPU or inside that coprocessor. So it's doing the allocation here, opening the memory buffers inside the device. Now here you are doing the copying on these arrays into those into the device. So from the CPU into the GPU. And here you are creating the program, the kernel, that is this function on top, this function here on top, this function. And I'm preparing that for execution. And the execution happens here. So at the very end, you are copying back the result. And this is the theme in CUDA very similar without that boilerplate code. Once you finish, you bring the results back to the CPU, back to the memory that the CPU is able to see. So it's copy that back to the CPU here. At the end, you are freeing the memory on the device. And you are freeing the memory on the CPU. So here is basically cleaning. And here in the middle, I am just printing the values for the array. So again, the advantage of OpenCL, and some people program OpenCL, I don't want to discourage OpenCL, but it's because the good advantage is that you can program a variety of different coprocessors, not only NVIDIA GPUs, but also other kinds of with the same code, with the same basic code. But that generality comes with a price. That's my point. So how you compile this with MVC? So if you try that like as it is, it will fail because you don't have the header. So you have to put the header OpenCL. That's the name of the header. And now, and this. And you need to add here the library, and it is in, where's that? Let me see. Okay. It's inside the CUDA, I think. Okay, I need to more load CUDA for this. CUDA is parallel, CUDA 11.1. ls md CUDA, yes, lib64. Okay, so here you will see OpenCL. This is what I'm looking for, OpenCL. So to compile this, it will be something like this. lib64. Okay, like this. So basically what I was missing was this, the location for this library. And I want something more. I want this info equal all. So it's not telling me. Okay. And here I am doing parallelization. I imagine that. Okay, I'm not printing anything. So that's how you write that. So now we enter in the last 10 minutes for today. OpenACC, which is very simple. And finally, CUDA, the first CUDA example. And for the next week, we will dig into CUDA programming for real. OpenACC is super simple. It's like OpenMP, actually. So you add some pragmas in some specific places that allow you to parallelize that code. OpenMP before version 4.0 was restricted to just parallelizing code on the CPU. Starting from 4.5, they allow to offload execution to GPUs if your compiler is capable of that. But OpenACC was created for offloading execution to the GPUs. So again, very, very similar. I think that's the only change on the code, as far as I know, from the top. Yes, that's the only thing. So, and I'm just parallelizing that section here. Very similar to OpenMP, or Pragma, or ACC. you say, okay, this is something that is shared. Or, by the way, this is something that you need to send to the GPU. A and B, please send A and B to the GPU. And this is what I'm copying back from the GPU. So it will update the value of C from the GPU. All of that without actually sending any, well, explicitly, you don't want to write all the code for sending from the memory, from the host to the device, from the device to the host, and all the operations, and writing a kernel externally, all that. You just write a single line, and you are doing all that for you magically, let's say. So it's very good for moving into GPUs code with minimal effort. So let's see how that works. It's actually very simple. MVC, so same compiler, DAXP, OpenACC. If I compile it this way, it will not be parallelizing anything actually. But this code is so simple that you will not even notice. But if I write info equal all, it will parallelize something else, I think. Let me see what it's actually. Actually, OpenACC. What is actually doing? Oh, it's parallelizing that thing, but not with the GPU. That for sure. So for parallelizing with the GPU, you need to put ACC here. So now, yes, notice that you have changed. You will be parallelizing line 37, so it's the loop. And you are generating code for the Tesla code, so it will be for the GPU. And you will be copying these variables to the GPU, and you are copying back the result of C from the GPU back to the host. You check that the loop is effectively parallelizable, so everything is fine. Each index is independent from each other, so you can do that. It's generating the code for the GPU, and it's telling you, okay, you can do that. And this is CUDA wording. You will understand that next session, what those block and thread means for CUDA. But this is actually parallelizing the code on the GPU. So again, I am a GPU. So I have one GPU core, and I can execute this code, and it's executing. It's actually taking longer because this is so simple that I'm paying a huge price, and well, not that huge, but there is some cost associated to sending a copy of that from the CPU, from the host to the device, to the GPU, and bringing that data back. So this code for sure is slower using the GPU than the CPU, than computing just from the CPU. But you got the idea. It's very good. It's a very cheap way of getting a nice code quickly using the GPU and exporting, getting all the power of the GPU for loops, for example. And finally, in the 4 minutes that I have left, what I will show you is the CUDA. So with CUDA, you are not effectively programming in C, actually. So technically, this is not directly C, so it's not C valid. There are several things here that depart from the language. So you cannot compile this code with a C compiler. You need to use the CUDA compiler. And the CUDA compiler at some point will call the C compiler. But that's behind curtains. All this that you are writing here is not C, well, not explicitly, but more importantly, this is not C. That's for sure. This is not C. C will complain about this. doesn't understand what those triple lowercase and this lower than and greater than means. It's completely out of the language. So you will not be able to compile that. You need to compile it with the CUDA toolkit. And that's what we'll be doing right now. So what is happening here? You need to allocate memory on the device. So that you do that with a CUDA malloc. This allocation is for the CPU. So this allocation for the CPU, and those that I put D underscore are on the device. That's the way I understand that those are in a different place on the device memory. So it will be part of those 24 gigabytes of memory that the CUDA GPU has. Here I'm copying A into the device. So it's a little bit counterintuitive because for those of you who are used to Unix, usually it's from source to destination, but this is the other way around. First the destination, after the source. So we are copying some arrays from the host, from the CPU, let's say, to the device, to the GPU. And here, this is something that we will devote most of the time next session. It will be arranging the threads, all the multi-threading. This is in GPUs, we are talking about many threading computing, thousands of threads eventually. So threads are organized in a grid. Several threads are organized in a block. This is you can imagine a three-dimensional arrangement of threads in a block. And blocks are arranged in three-dimensional arrange called a grid. So that's how CUDA manage eventually thousands or hundreds of thousands eventually threads that are working concurrently, all in a concerted mess to solve the problem. And this is how you decide, okay, I would like to create 32 threads on a block, and I would like them to be in one dimension. So there are 32 threads on one dimensional arranged in a block. And blocks will be also arranged in one dimension sets. And this is how you compute how many you need to build the grid. How many blocks do you need total? And here is where you are actually executing the function. The function needs 4 elements. Alpha will work with the A, B, and C that sit on the device. They will do all the operations. And at the end, I will copy back the data from the device to the host. Notice that this operation starts happening on the device. As soon as it starts launching, it returns the operation to the CPU. So the CPU can continue to do some other stuff. All the cores in the CPU can process all the data, could do other things, until you reach a barrier. This CUDA copying back is a barrier. It's waiting for this function to finish before copying the data back. So this is actually effectively stopping the execution for the CPU until you can copy all the memory back. And here I am printing the results. And here I am freeing the memory on the host, so for the CPU, for the RAM. And here I am freeing the memory for the device. So deallocating all that from the GPU, so I can finish cleanly my execution. How you compile this? Very well. MVCC, the CUDA compiler. Notice a double C here. And DAXP, CUDA, Q. And I execute this. And voila. It's running all the computation for the C was done in the GPU. It brings back all the data, and it's done. So for the next week, we will understand better all that, the grid, the blocks, and the threads to better follow what it means to program in CUDA. And if I can also explain more about OpenACC, probably we'll start balancing that so we can move into higher levels of languages and eventually explain PyTorch and TensorFlow. So how those things build up until a big code, for example, for deep learning. We will see how far I can go with that. So that is for today. I will stop sharing my screen and see you next week. And thank you, Alfredo, for being here. So otherwise, I will be okay. I don't know. It's okay. So Nick, Daniel, eventually could have something they wanted about this.